Is about top k frequent elements, and the problem statement is that let's suppose you have an array of some elements. So we have 1 1 1, then we have 2 2, and then we have 3, and then we have a value of k such as 2. So we are going to return k frequent elements, and we can see that 1 is occurring 3 times, 2 is occurring 2 times, 3 is occurring 1 time. So most frequent elements are 1 and 2. That is what the problem requires, and this is also one of the classic interview problems. So before we start discussing the solution, let's try to recognize if there is some kind of pattern in this problem or not, and we can see that whether this problem is actually a top k pattern problem or not. So let's just take a look in that, and we know that we are supposed to find out k most frequent elements, and the second thing is we need to find k specific elements, and we do not need all the elements. So this is what actually hints us that this might be a top k pattern problem. If you have watched the videos where I shared my thoughts around kth largest element, and we also had a video where we walked through k closest points to origin, you will be able to see that the problem that we are dealing right now, k most frequent elements, it's similar to these one, and you might also be already thinking that this feels familiar. So let's talk about our approach for the naive solution, and the naive solution is just very straightforward. The first step would be just to count frequencies. So we have 1 as 3, 2 as 2, 3 as 1, and then you just sort on based of frequencies, and that's how you actually return the value. So if we talk about space complexity and time complexity, so the time complexity for building a hash map, it's just big O of n. So the time complexity for Hashmap would be big O of n, and space complexity would be big O of n as well if all the elements in the array were already unique. So you will have to definitely build a hash map for every element. And if you talk about the sorting part, time complexity, it's going to be n log of n, and the space complexity is going to be constant in case you opt for an in-place sorting algorithm. So that's how the naive solution looks like, very straightforward. If I have to see how can I improve the time complexity over here, then what I will have to think is that what is actually taking a lot of time, and clearly it's the sorting part which is clearly taking a lot of time. And let's suppose if n unique is 1 million elements and k was 10, that would mean we are trying to sort out 1 million elements just to find out 10 most frequent elements. So this is the bottleneck, and if you want to improve this, we might need to think in terms of a solution which is not related to sorting. And if you think about the videos where we discussed kth largest and we talked about k closest points to origin, the bottleneck that we have in this problem where we are sorting everything just to find that k, just to decode that value of k, it's the same bottleneck over here as well. So how do we avoid sorting all the unique elements? That's the core problem that we are trying to optimize if we want to bring down this time complexity. And here is what a simpler solution or a better solution could look like. We'd actually track only k elements. Second would be, how can we process the unique elements efficiently for comparisons, that which one is greater, which one is not greater in terms of frequency, and how can we actually bring down this n log n based on what I have said in 1 and 2 to actually n log of k, because I cannot decrease n, I still will have to traverse the entire array. So log n is something that I might be able to optimize. And I know that heap is a data structure where every push and pop operation is going to be in log of k times. And it can also allow me to keep track of only k elements, track of only k frequent elements. So let's see how can a heap help us and how can a minimum heap help us. I'm going to move towards the optimized solution. It will also become clear why we are opting for a minimum heap and why we are actually not opting for a maximum heap. So I'm going to draw the elements again that we had in the original array and with k is equals to 2. So the first step was to actually build a hash map. It's the same. So we have 1 with frequency 3, then we have 2 with frequency 1. We have 3 with frequency 1 and 2 with frequency 2, not 1. Let me just make it clear. 3 with frequency 1, and let's just assume for the sake of example we also had an element 8 with value 10. So which elements are actually the most frequent ones? We have definitely this one and this one. So the output should be 1, 3 and 8 and 10. This is what I'm actually looking forward to. So I'm going to move towards dry run now, and I'm going to draw the heap state as well for your visualization. So my first element is 1 and 3, and I'm building my heap map. I'm building my minimum heap, not the heap map. I'm building this minimum heap based upon frequency. So I have element 1 and frequency 3, element 2 with frequency 2, element 3 with frequency 1, element 8 with frequency 10. So I have an empty heap, so I'm just going to push it because the heap is empty. And now the size of the heap is 1, so I'm pushing 3 in my heap. So far so good. And now I have 2, 2, and my heap is not full. By full I mean, is my heap current size equal to k or not? Because remember, we decided we are actually going to keep track of only k frequent elements. So that's why the heap size is important to consider. So currently my heap size is 1, and I have an element 2 with frequency 2. It's the frequency that we are building our heap on. So I'm just going to push 2, and it's a minimum heap. So 2 is actually pointing to this, and this 1 and 3 is where we have this 3. And the heap size is full now. Now I have 3 and 1 coming in. And this is where you will be able to understand that why we decided to build a minimum heap as compared to a maximum heap more clearly. So the frequency, incoming frequency is 1, and the frequency at the top of the heap map currently is 2, which you can see here. So what I'm trying to see is that at any given point in my heap, I'm just going to keep track of the frequent ones. And because it's a minimum heap, so I have a boundary or a guard at the root level, which is always going to be smallest of all the largest so far. This is a very, very key concept that will help you understand why to go for a minimum heap. So I do know that I have 2 as minimum, smallest of the largest. So when I talk about incoming 1, so I would say, is my 1 greater than 2? It's not. Then that would give me a hint or an indication that don't change heap. Then that would mean that the guard or the boundary of the heap, which is root, it is doing what it is supposed to do, and this is smallest of the largest. And up till now there were no elements whose frequency was greater than the smallest one. But now let's see what happens when we have 8 and 10. So we have 8 and 10, and now I do know that my heap size is full. So again, I'm going to make a comparison call, just similar to how we did. We can't just blindly push it. And I would see, is 8 greater than 2? Yes. And then I would pop 2, I would push 8, and the heap would become something like this. And this is what we actually wanted as well. So this 3 is for 1 and 3, and this 8 was for 8 and 10. And it's again frequencies that I have listed in the heap. And these again are making sure that at any point given in your heap, you only have k most frequent elements. And the reason for minimum heap I have already mentioned. You always make sure that this is smallest of all the largest. So every incoming element only needs to be compared to the root node instead of being compared with every element. So this is where we are having that efficiency in our algorithm. So now let's quickly talk about the space complexity and time complexity of this heap. So the heap is actually based upon pop and push operations, which are each log k. How many times can you have this push and pop operations at maximum? The maximum size can be n, so it can be n log of k. And if you talk about time complexity of building your hash map, it was definitely big O of n. Let's talk about space complexity. For the heap map, the biggest size that you can have at any time is going to be k. So that's the space complexity, and for the hash map, it's going to be big O of n. So the total space complexity is going to be n because that is what it is dominating. And for this one, we are going to have n log of a when we add both of them. So one last note before we end this video. If we talk about the previous videos that we have seen regarding kth largest element and k closest points to origin, they were also following the same pattern where we had to find kth largest element and we had minimum heap again of size k, and for k closest point we were trying to actually find k smallest distances, but we had a maximum heap of size k. And in this current problem of top k frequencies, we were actually trying to find out k largest frequencies and with minimum heap size. So this is same set of problems with different slight wording or just some different kind of strategies that we have used, but at the very core, the core optimization of building a heap and then deciding whether it's a minimum heap or a maximum heap, that's the same thing. And the other same thing is that it's just more about the top k pattern problem. So that's it for the video, and see you in the next one.